Introduction to Solutions in Aqueous Reactions, reviewing redox and simple redox reactions. In this tutorial, we will be talking about how to define oxidation and reduction reactions, recognizing redox reactions, practice, oxidation of metals by acids and salts, some examples, and then finally some more practice. So let's start out with a quick review of oxidation and reduction reactions. So oxidation is the loss of one or more electrons. And remember, electrons are negatively charged. This will result in an increase in oxidation state, such as 0 to +1 or +1 to +2. Metals tend to be oxidized and form positive ions. And the example that we're going to look at is lithium with an oxidation number of 0, going to lithium with an oxidation number of +1, and therefore losing one electron because my oxidation numbers are becoming more positive. On the other side, we have reduction. Reduction is gaining of one or more electrons. We'll see a decrease in the oxidation state. Nonmetals tend to be reduced and gain electrons to get their full octet, and they will form negative ions. So the example that I have here is a bromine atom, which we know has 7 valence electrons, gains 1 electron, and becomes bromine -1 with its full octet. So the oxidation numbers change from 0 to -1. All of this is based upon your understanding of how to assign oxidation numbers, how to recognize a redox reaction. So the first step always is to assign oxidation numbers to all of the elements. So if I look at this chemical equation, I can look at Mg and say, well, that will be 0, Zn is going to be +2, Cl is going to be -1. On the other side, Mg is going to be +2, Cl is going to be -1, and Zn is going to be 0. So I've accomplished my first step. Step 2 is to examine the elements to see if a change in oxidation number occurs as you go from the reactant side to the product side. And we can see that this definitely happens here. Mg is going from 0 to +2, while Zn is going from +2 to 0. So as we go from reactants to products, a change in oxidation number has taken place. So if a change in oxidation number occurs, the reaction can be labeled as a redox reaction, just like we see with our example above. But if a change in oxidation number does not occur, and that definitely happens, the reaction is not a redox reaction. How to recognize a redox reaction? A little bit of practice. So what I'd like you to do is stop the video for a moment, go through, assign oxidation numbers to all the elements in all the reactions, identify whether you think they're a redox reaction or not, and then come back and check your work. Welcome back. Let's see how you did. So H2 is going to be 0 because it's diatomic. I2 is going to be a 0. And then the compound HI, H is +1, I is -1. This is a redox reaction. Let's look at our next one. Ag is going to be +1. Oxygen is going to be -2. -2 times 3 gives me -6. Bring the +1 down because there's an assumed 1 right there, which means nitrogen has to be +5. NaCl. Na is +1. Cl is -1. AgCl. Ag is +1. Cl is -1. NaNO3. Na is +1. Oxygen is -2. -2 times 3 gives me -6. Bring the +1 down. That means the nitrogen has to be +5. So when we look at this situation, we notice that as we go through the elements from reactants to products, they don't change. Ag is +1 here, +1 here. Nitrogen is +5, +5. Oxygen is -2 on both sides. Na is +1 on both sides. And Cl on both sides is -1. So this is not redox. We could call this a double replacement reaction. We could call this a precipitation reaction, but it's not a redox reaction. Let's look at our next example. Cl2 is 0. K is +1. Br is -1. K on the other side is +1, Cl is -1, and Br2, because it's diatomic, is 0. So when I compare reactants to products, Cl is going from 0 to -1, K is +1 and +1, so that's not changing, but Br is -1 to 0. Therefore, this is a redox reaction. Redox. We're seeing a change in charge. Something's being oxidized, something's being reduced, and we'll go into more specifics on that in a little bit. Finally, our last example. In the compound NaCl solid, Na is +1, Cl is -1. It is added to water and dissolved, where we have sodium ions and chloride ions. This is not redox, redox. It's a physical change, not a chemical change. So don't get thrown by that. If the charges don't change, it's not a redox reaction. Oxidation of metals by acids and salts. Redox reactions are commonly occur as a single replacement reaction, which we will review in detail in the future, where you have a single element, some type of ionic compound in an aqueous solution. The single element, if it is more reactive, comes out and kicks out the less reactive element, so it's by itself, and then that more reactive element forms a new compound or goes into solution. So many metals undergo single replacement reactions with acids, producing chemical salts and hydrogen gas. Here's two examples. I have solid magnesium placed in nitric acid. We can see here that the magnesium is going to kick out the hydrogen gas is produced, and the chemical salt magnesium nitrate is formed. Then we have calcium. Same situation. Calcium is going to come in, it's going to kick out the hydrogen, it's going to form hydrogen gas, and the compound CaCl2 is one of our products. Again, it's very soluble, it's going to form ions in solution, but as a representation here as a single replacement reaction, we're going to call it CaCl2. Let's start out by looking at our molecular equation. Fe plus 2HNO3 yields FeNO3 and H2, and we can see that it's already balanced. So before we get into assigning oxidation numbers, let's break this down into an ionic equation to see if we can separate out or identify any spectator ions. So Fe by itself, Fe, nitric acid is a strong acid, so we're going to have plus 2H plus 1 plus 2NO3 minus 1 yields. Fe here is going to be plus 2 because we're going to take this and uncrisscross it, plus 2 because we don't want to forget this subscript right here, NO3 minus 1 plus H2. Now that we've done that, let's go and cross out any spectator ions that we see. So 2NO3 minus 1, 2NO3 minus 1, we've crossed out our spectator ions. For our net ionic equation, this time I am going to put charges on anything that is now currently lacking a charge. So we know that Fe is going to be 0 plus 2H plus 1 yields Fe plus 2 plus H2, which is a diatomic, which we know will have a charge of 0. So that's our net ionic equation. When we talk about the oxidation half reaction, we're looking for our oxidation number to become more positive. So if we look at Fe, Fe is going from 0 to plus 2. That's becoming more positive. So when we write our oxidation half reaction, it's going to be Fe0 yields Fe plus 2 with a loss of 2 electrons. Now let's look at the reduction half reaction. With the reduction half reaction, we need a decrease in oxidation number. So H plus 1 going to H20, that is a decrease in oxidation number. So I'm going to write 2H plus 1 plus 2 electrons. So each hydrogen ion gains an electron to form the covalent bond in my diatomic hydrogen. So I can see that my oxidation numbers have decreased. When we talk about what species is specifically oxidized or reduced, we always look at the reactants. So what is being oxidized is Fe0, and what is being reduced is the H+1. If you want to put the 2 in front of it, that's fine, but we are looking specifically at the reactants when we talk about what's being oxidized and what's being reduced. Let's look at our next example. Our molecular equation is 2Al plus 3NiSO4 yields Al2SO4 and 3Ni. So we can see that it is already balanced, and our ionic equation is going to be as follows. So 2Al plus NiSO4 is soluble in water, so 3Ni plus 2, because we're going to have 3SO4, and we know that sulfate is -2, so that is how we can realize that Ni is going to be +2, yields 2Al plus 3, because the +3 charge is something that you should be familiar with, and we want to make sure that we take this subscripted 2 and put it as a coefficient in front, and then 3SO4 minus 2, because we have 3 moles of this, so don't forget that subscripted 3 is going to go in front of your SO4 minus 2, plus 3Ni. The final thing that we want to do here before we move on to our net ionic equation is to cross out any spectator ions that we have. So 3SO4 minus 2, 3SO4 minus 2, those are crossed out. So when I rewrite my net ionic equation, if there's any element that does not have an oxidation number, I'm now going to include it. So 2Al0 plus 3Ni plus 2 yields 2Al plus 3 plus 3Ni0. Fantastic. Now let's go on and talk about what is being oxidized and what's being reduced and how we're going to represent that. If we look at Al, it's going from Al0 to Al plus 3. My oxidation numbers are increasing, meaning that I am losing electrons. This is what's going to be oxidized. So 2Al0 is what is specifically oxidized, yields 2Al plus 3 with a total loss of 6 electrons, not 3 electrons. Each aluminum atom is going to lose 3 electrons, but because we have this 2 in front, our total loss is going to be 6 electrons. 3Ni plus 2 plus some number of electrons will give us 3Ni0. Now, Ni plus 2 to Ni0 means we're gaining 2 electrons. But because we have this coefficient of 3 in front, that means we are gaining a total of 6 electrons. Sort of had to jam that in there a little bit. So because we had the chemical reaction balanced ahead of time, it makes sense that the number of electrons lost equals the number of electrons gained. So what species is oxidized? Al0 is being oxidized, or you could write 2Al0. What species is reduced? Ni plus 2, or again, you could write 3Ni plus 2 as what is being reduced. So what did you learn? We went over the definitions of oxidation and reduction, little review. We learned how to recognize a redox reaction by assigning oxidation numbers. We did some practice with that. Then we talked about oxidation of metals by acids and salts, showed you some examples, and did some more practice. Need more help? Feel free to contact me. Have a great day.